In this video, we're going to relate directional derivatives to the gradient. And we'll see that the gradient points in the direction of greatest ascent of a function. And I'm going to state a theorem that makes that precise and also prove it. The proof that I've seen in books is a bit complicated and not very intuitive, but the result is actually pretty intuitive. So I want to give a different proof that is more intuitive. Okay, so now I'm going to start with the function f, which is a function from R2 to R. Your function doesn't actually have to be defined on all of R2. It could just be defined on an open set of R2, but for simplicity, I'm just going to assume that f is defined on all of R2. And we recall what it means for this to be differentiable. So this function, let's say this is a function f of xy, this is differentiable if its partial derivatives exist. So say at a comma b, it's differentiable at a comma b if the partial derivatives f sub x at ab and f sub y at ab exist, and when you take the difference f, let's say f of xy minus the linear approximation, so this is at ab, so f of ab plus f sub x at ab x plus f sub y of ab y, this divided by the length of the vector xy, that if this limit goes to 0, okay, I should say that this is x minus a, sorry, and this should be y minus b, and then this should be, oops, x minus a squared plus y minus b squared, and take the square root, as this goes to a comma b. If this limit is equal to 0. Okay? So basically what's going on is this part is, you think of this as the linear approximation to f at a comma b. You're approximating your function of two variables with a linear function. So, right, because what's going on is this f of ab, that's a constant. That's like c1 plus, and f sub x evaluated at ab is like some other constant, like c2 times x minus a plus f sub y of ab is another constant, c3 times y minus b. That's a linear function in x and y. Okay, so the idea is that the difference between f of x, y, right, your function, and the linear function, it's not just that the limit of that difference goes to 0. It's the limit of the difference divided by the length of the vector from ab to xy goes to 0. That quotient goes to 0. And this is not a very intuitive definition, but it's the definition that generalizes the definition of a differentiable function in Calc 1 for a function of a single variable. and it's the definition that has nice properties. And one of the things we'll see is that this implies some nice facts about the gradient. Okay. Maybe one more thing I'll add is that the condition in that this limit is 0, it's important that you have this denominator, the square root of x minus a squared plus y minus b squared. Because if you didn't, if you just got rid of that and just took the statement that the limit of the difference between the function and the linear function is 0, well, that would apply to any linear function that has the same value at a comma b, right? So if you have a function of a comma b, the idea is that the graph is approximated by a tangent plane. But if you just took any plane that intersected the graph of f at a comma b, then it would be true that the limit of the difference would be 0. So somehow this quotient is important in the limit definition of differentiability. Okay. And sometimes this function, this whole function in the numerator is sometimes called R1 of x1 because it's the remainder. It's the first order remainder of the function when you subtract the linear approximation. Okay. And there's R2 and R3 and so on. That comes from the Taylor expansion of the function. So you can have first order approximation, that's this linear approximation, but then there's a second order approximation that involves x minus a squared and y minus b squared. And then when you subtract the second order approximation, you get R sub 2. So that's where the R sub 1 comes from. So one way to say this is that when you take the error, R sub 1 of xy, and divide by the length of the vector from ab to xy, that the quotient approaches 0. Okay. So what's going on in terms of the picture is you have x-axis and the y-axis, and you have a function defined on R2, right? This is R2, and you have some point a comma b, and you're saying what happens to the function near AB. Okay. And I'm also skipping some things under the rug. I'm sweeping some things under the rug because technically it just needs to be in the neighborhood of a comma b, right? So for all x, y in the neighborhood, let's just say sufficiently close to a comma b. So if for all x, y sufficiently close to a comma b, the partial derivatives exist and this limit is equal to 0. Then we say the function is differentiable at a comma b. All right, so that tells you something about the directional derivatives. So to say what this tells us about the directional derivatives, let's assume for simplicity that f of ab is equal to 0. Okay, and also that a comma b is just equal to 0, 0. This helps simplify things a lot in terms of the notation. So what we have is R2, and you have a function that's differentiable at 0, 0, and the value of the function at 0, 0 is equal to 0, and you want to know the directional derivative of the function in the unit vector, in the direction of the unit vector, say xy. Okay. So that's a unit vector. And the question is, what's the rate of change of the function in that direction? Well, that's given by the directional derivative, right? So the directional derivative of f in the direction of the unit vector xy is, well, it's defined to be, okay, so d sub xy of f, okay, this evaluated at 0, 0 is equal to, by definition, it's the limit as t goes to 0 of f of, so you take your a comma b and then you add t times that vector. Well, that would just be f of tx because it's 0, 0 plus txy, right? So it's tx comma ty. That's your new input that you put into the function. And then minus f of a comma b. Well, in this case, a comma b is 0, 0. And we're assuming that f of 0, 0 is equal to 0. So you just get f of tx, ty divided by t. Okay. Well, since f is differentiable, okay, actually we're not using the differentiability yet. At this step, we use the fact that, okay, we define r sub 1 of xy to be the difference of f of xy and the linear approximation. So if we do that, we're going to get, well, f of 0, 0, that's 0, and then plus partial f, partial x evaluated at 0, 0 times tx plus partial f, partial y evaluated at 0, 0 times ty plus the remainder, r sub 1 of tx comma ty. Oh, I didn't leave enough space. This. Oops. R sub 1 of tx comma ty. This divided by t. Okay, that's just the definition of R1. And now, now I can split this up, because what happens is we know that the limit as t approaches 0 of this part, this quotient is equal to, well, we'll see what that is in a second. So we can split up this thing into the limit as t goes to 0 of partial f, partial x, 0, 0 times tx divided by t, plus the limit as t goes to 0, partial f, partial y, at 0, 0 times ty divided by t, plus the limit as t goes to 0 of r sub 1 of tx comma ty divided by t. Of course, this is assuming that the limit exists, but we're going to show that the limits exist. So in the first term, the t's will cancel, and in the second term, the t's will cancel. So then what you're going to be left with, since there's no more t's left, the first term is just going to be partial f, partial x evaluated at 0, 0 times x. Second term is going to be partial f, partial y at 0, 0 times y. And then you're going to get plus this last limit. Now I'm going to evaluate this last limit, I'm going to let u equal tx and v equal ty. Okay. So what's going to happen is when you do that, to say that t approaches 0 is to say that u and v are approaching 0. So this is the limit as u comma v approaches 0, 0 of r1 of, so tx is u, ty is v, and then t is t is the magnitude. T is the magnitude of the vector u comma v. So it's u squared plus v squared, well, the square root of u squared plus v squared. Okay, why is that? Because x comma y is a unit vector, right? We assume that xy is a unit vector. And so that's where this comes from, right? If you take u squared plus v squared, you just get t squared times x squared plus t squared times y squared, and you factor out the t squared. So you get t squared times x squared plus y squared, and then you take the square root, and then you just get t times the square root of x squared plus y squared. Square root of x squared plus y squared is 1. Now what is this limit equal to? This is where you use the fact that your function is differentiable. Right? Your R1 has the property that this limit of the quotient is equal to 0. And so since f is differentiable, so what we've discovered is that the partial derivative of f in the direction x comma y is just equal to the partial derivative at 0, 0 x plus the partial derivative at y at 0, 0 times y. And in general, the partial for any differentiable function f from R2 to R, the directional derivative in the direction x comma y of f evaluated at a comma b is just equal to partial f partial x at a comma b x plus partial f partial y evaluated a b times y by the same reasoning. Because the only difference is when so the 0 comma 0 is going to turn into a comma b, and then other than that, there's no real difference in the argument. It's just bookkeeping of the notation. Okay. So let's put this in a box. So this is an important result because it says, so one way to think about this is that this is equal to the dot product of partial f partial x at AB, partial f partial y AB, this vector dotted with, it should be, I keep forgetting this, it should be x minus a, right? And then y minus b. Yes. So it's this dotted with the vector x minus a, y minus b. So if you're at a comma b, let's say a comma b is here, and then you go in the direction x comma y, so that vector is x comma y, then wait, no, is this right? No, it should be just xy. It should be just xy. Sorry. It's just dotted with this unit vector. So if this unit vector is called u, then this would just be, well, the first one is the gradient. It's the gradient of f evaluate AB dotted with the unit vector u. So that's the theorem. So one consequence of this is if you wanted to see, okay, you have this function at a comma b, and you want to know, okay, in what direction, which value of u maximizes the directional derivative. Because you get one directional derivative for each direction u, and the question is, out of all the different u's, which one will maximize the directional derivative? Well, the dot product is equal to the length, so the magnitude of this first vector times the length of the second vector. Well, the length of the second vector is just 1 because it's a unit vector, and then times cosine of theta, where theta is the angle between the two vectors, right? So you have, partial f, and AB is this one vector, and then u is some other vector, and then theta is the angle between them, right? So all you can change is theta, because you can't change a and b and f. You're given a and b and f. The question is, okay, which theta should you pick? Well, remember that cosine of theta is always between -1 and 1. So the biggest value of this is when cosine of theta is 1. So this is maximized when cosine of theta is 1. Well, what theta makes cosine equal to 1? 0, right? i.e. when theta is 0. So this tells you that the answer is when theta is 0. Well, when theta is 0, that's when the two vectors are like this, right? When the angle is 0, that's what happens. So when u is in the direction of the gradient, okay, when u is pointing in the same direction as the gradient vector, okay, then the directional derivative is maximized. So, yeah, the direction of the gradient, meaning the gradient evaluated at a comma b, that vector. So what's that? Well, that's when, so u is a unit vector, so you take u to be, you take the gradient vector, right? So you take the gradient evaluated at a comma b, you get that vector, that's the gradient vector. And then to make it a unit vector, you divide by the length. So this is the vector that will maximize the rate of change of your function. So if you have a function f of xy and you want it to go, you want it to increase as quickly as possible, you should move in the direction of the gradient. And what about in the direction of, if you want to make f decrease as fast as possible, or at least to maybe increase as least as possible if your function can't decrease. So then the direction of the direction at which your function decreases the fastest, right? So the direction of steepest decrease is, well, when you minimize this value, and that's cosine theta is minimized when cosine theta is -1. And so it's when cosine of theta is -1, that is, i.e., okay, when is cosine theta equal to -1? When theta is equal to 180 degrees, or pi, right? So in that case, your vector u in the direction of steepest decrease would be minus the gradient divided by the magnitude. So in other words, it's in the direction, if the gradient is this way, then you want your u to be in the opposite direction. And the direction where the directional derivative is 0, so you want your function to have instantaneous rate of change of 0. Which direction should you go? That is when cosine of theta is 0, right? Because if you set this equal to 0, you just get cosine of theta is 0. Cosine of theta is 0 is when theta is 90 degrees, or pi over 2. So in this case, if your gradient is this way, then you should be going perpendicular to the gradient. So you get a 90-degree angle. There's also some intuition behind why this is true if you think about the function f of x, y in terms of a planar function. So if your function is, so some more intuition behind this is, if your function, so the idea is that your function, the graph, okay, is approximately a plane. And so in this case, your function is like, C1 C1 of x minus a plus C2 of y minus b, or something. Right, it's like f of a comma b plus that. And the gradient is just C1, C2. So this is saying that your function in the E1 direction, right, in the direction of 1, 0, your function's increasing at a rate of C1, and in the E2 direction, 0, 1, your function is increasing at a rate of C2. And if you go in a certain direction, like if you go this way, x comma y, then the rate of change will be the gradient. So if you go this way, f is increasing at a rate of C1x plus C2y. So it'll be some combination of C1 and C2, right? And that gives you some intuition behind what's going on. So I would try to work this out if your function is if the graph of the function is a plane, and then try to get some intuition behind, why you would do this. And that will give you some more intuition behind why the formula makes sense. Okay, we'll do some more examples of this in another video.